Hey guys, what's up? Just a small experiment here. A simple signal generator which can generate these three waveforms: sine, square, and triangle. So, just a block diagram here to illustrate which circuits we're going to be implementing. So, it's just three separate circuits cascaded to get these three waveforms. We have the Wien bridge oscillator, which is a classic sine wave oscillator to obtain a low distortion sine wave. Then we have a Schmidt trigger circuit which works on hysteresis, and we get a reliable square wave between the upper trigger point and lower trigger point. And lastly, we have a integrator which will integrate the waveform which you give at the input. So yeah, and all of these are going to be implemented using op amps, since those are very handy and we know how they work. So now that we know how the block diagram is, I'll just show you the schematic in Multisim, which is a nice software where we can just design our circuits and even simulate it if you want. So first here, this till here, we have the first stage. So this is our Wien bridge oscillator, and the op amp which I'm going to be using here, let me just show you that. This is the op amp which I'm going to be using, the TL074. It's a good JFET based op amp, and as we know, it's since it's JFET, it's going to have very high input impedance. So we like that. It's going to have low input bias current and in general low power. So it's good for any general purpose application, low power consumption, and the slew rate is quite good. It's a 13 volt per microsecond, so that's good. And I think it has around 3 megahertz bandwidth gain. Maximum bandwidth, so that is also good for this. Yeah, this is a nice op amp for general applications. So this is the pinout, and we're going to be needing three op amps here. So the 074, as the name says, has it's a quad op amp, so four op amps in one package. So yeah, we'll be using three of these four op amps. So now back to the circuit. This is the Wien bridge, and according to the formula, you can choose the frequency. This is Wien bridge is generally suitable for low to medium frequencies. So right now I've designed it for around 1 kilohertz. So according to the formula, 1 by 2 pi RC, as we know, we're gonna choose the R and C values. This is a RC based oscillator. So yeah, I got 120k and 1 nanofarad. So that's what we're gonna be using. Two in parallel and two in series in the non-inverting input. So that's what the feedback or feedback tank is, and just a 10k in input, but the input is just going to be grounded on one end, and we in the non-inverting feedback we have a 18k and a 10k pot, and that pot is actually just for adjusting the gain, since we know the Wien bridge, according to the Barkhausen criterion, which says that A beta must be equal to 1, yeah, the Wien bridge needs a very precise gain of 3. So to just fine tune that, I've added this pot here, so that is useful to prevent the sine wave from going into saturation or becoming distorted. We for just adjusting the proper sine wave, we have the pot there in series. So that is the first stage. After that, we have here the simple Schmidt trigger. It's a very inverting Schmidt trigger configuration, by the way. So that's why the input is going to the inverting terminal, and the non-inverting input just 1k and 10k to just adjust the gain. This is pretty straightforward, not much to explain here. According to the formula R2, which is the feedback, so R2 by R1 plus R2 into whatever your upper trigger point. So your rail is here, your two rails, you're going to get the hysteresis output. So that is the Schmidt trigger. And the last one is the integrator here. There, the non-inverting, I mean the inverting, yeah, the non-inverting input is basically grounded. We don't need to do anything with that. So inverting input, we give 10k and 68 nanofarad, and this actually I calculated again. The as the integrator works using its name, it basically integrates whatever waveform you give it. So that formula is, since it's in the inverted configuration, the formula is minus 1 by RC integral of whatever input voltage you give. So though that RC value, again, you need to decide according to what the square wave you have, basically one half period of that. Depending on that, you choose the RC value using the time constant. So if you make it too high, your amplitude is basically going to get more and more attenuated of the peak to peak output of the triangle. And if you give it too low, then again it's going to get clipped. So you need to choose that value properly. So just again optimize that value as per your need. So here I chose 10k and 68 nanofarad. And one important thing is, in an ideal integrator you just have a series R and a feedback C. That is an ideal integrator. But for practical purposes, as we call the practical integrator, we need to put a higher value resistor in parallel with that C. And that is because the output, there's always going to be a, if as soon as there's a DC offset, as we say, DC offsets are not good. It's the op amp is basically going to latch onto that, and your output is going to saturate to one of the plus rail, most likely plus VCC, and then you're not going to get any triangle wave output. So to prevent that, we have this higher value resistor, and that generally, as a thumb rule, we choose it as 10 to 20 times the series resistor. So I just chose 10 times, and I checked that and it worked out. So maybe depending on how the temperature is and all, the output is going to drift. So we want to control that. So that's why we need to add this to prevent drifting specifically. So yeah, this is there over here. So now that the basic schematic is done, explanation, let's move to the breadboard circuit here. Yeah, so this is the breadboard circuit I've set up here. Just may look messy. I know there may be a lot of wires, but yeah, I'll just break it down the same way you saw it in the schematic. There I have the TL074. I think you can see it. That is the quad op amp, and basically these are those 120k and 1 nanofarads for the Wien bridge here. So I've taken these film capacitors. They have nice temperature stability over a wide range, so they are good. And all the resistors I've used here are 5% standard, 5% gold band tolerance resistors, so widely available. So yeah, this is the 120k. This is that feedback pot which I said for adjusting the gain. And yeah, so this part is going to be the Wien bridge. Then for the Schmitt trigger here, we have the 1k and the 10k there, as we know, the inverting Schmitt trigger. And lastly, we have here the integrator is on this end over here. So we have the the series resistor of 10k and the feedback 100k, as I said. And on the side there, I'm not sure you can see it, but yeah, that's the 68 nanofarad feedback capacitor there. I think it's a bit blur, but yeah, I think you get the point. So that is the basic tank. And another thing is, just to show you what setup I have here. As we know, op amps need, this is all bipolar, so we need a plus VCC and minus VCC. So I have two supplies here basically. This is a ready-made supply which I've bought, 12 volts, and this is an adjustable supply here using a pot. And this actually I've made it myself, this power supply. It's a regulated power supply. So this also I'm going to be setting it to around same 12 volts. So when we have two supplies, basically if you common ground between them, so basically you have this positive terminal here, you have this negative terminal, so and this has positive and negative. So these are the DC outputs, as we know they're DC supplies. So if you tie the negative of this to the positive of this, basically you're going to have a common ground. So if you check that common ground with respect to this, you're going to have plus VCC, and with respect to this negative, you're going to have a minus VCC. So that's how you can set up a dual supply here and give it to the op amp. So that's exactly what I've done here. This is the common ground rail on the breadboard, and this is the plus VCC and minus VCC I've done here and given it to the op amp. So now that our explanation is out of the way, I'll just show you some waveforms to make sure to show you how it works. So this is just a home oscilloscope I have here. It's a battery oscilloscope, not a bench top, so it's isolated from the ground. So yeah, I'll just switch the circuit on here. So yeah, switched on the circuit here. So you can see this is on, set to 12 volts, and yeah, this is around 12.5, 12.8 just set. And this is my oscilloscope probe. The ground is already connected to the common ground. We'll just connect it to the first sine wave here. So yeah, so I'm just going to connect it over here to the sine wave. So you can see this is you can see it's very low distortion. It's almost a perfect sine. You can see as you can see, there's slightly a bit of very slight amount of clipping here, but yeah, we can adjust that using the gain. That's why the pot is there. But yeah, for now it's good enough, the sine wave. And you can see we designed it for around 1 kilohertz. So yeah, we're getting almost exactly 1 kilohertz, so that is good. And 22 volts peak to peak, and that makes sense because we have a 12 volt and 12 volt. So yeah, 24 volt ideally, but yeah, there are going to be drops and such. So 22 volts is good enough. So this is the Wien bridge, which is working perfectly. And second, I'm going to move to the Schmidt trigger here. Let's plug that in. You can see this is the square wave, inverting the inverted square wave. And similar, we're going to have peak to peak similar voltage. And yeah, you can see this is the upper trigger point, lower trigger point. So we have the bipolar square wave here. Again, 1 kilohertz, the frequency is going to remain same. So yeah, this is the Schmidt trigger. And lastly, the integrator, the triangle wave. So yeah, we have the triangle wave here, and you can see visibly that the it's a nice triangle, you know, the ramp, basically a positive ramp. Whenever the square, that's what it's doing, whenever it's getting the positive cycle of the square wave, you're going to have a positive ramp, and in negative cycle a negative ramp. So that's what integration basically does. So you have the square wave here, and you can see visibly that the peak to peak voltage is much lesser, and that is again because of the same thing. The RC values, depending on what you choose, the it's going to be visually attenuated, as they say. So yeah, depending on your value which you choose, the amplitude you can increase it, but again there's a risk of clipping. So yeah, you need, in all of these analog, you need to be a little careful about that, otherwise you know the waveform just get distorted. But yeah, I can just increase the amplitude here if you want. So yeah, I made it around what is that, yeah, around 2.5 volt for division. Now you can clearly see that it's a nice triangle wave. So yeah, so the three, we covered the three waves here. We have the triangle, we have the square, and we have the sine, as we saw. So yeah, now that we saw all the three waveforms, I hope the explanation was clear. So yeah, thank you guys.